System calls stand at the heart of any modern operating system, acting as carefully maintained gateways between user applications and the privileged operations carried out in the kernel. From reading files on a hard drive to launching new processes, system calls enable user-level software to tap into powerful core functionalities while preserving overall system stability and security. In this narrated piece, we shall immerse ourselves in the essential principles, historical context, and practical significance of system calls within a typical Linux environment. By the end, you should have not only a theoretical grounding, but also a tangible sense of how system calls underpin our everyday interaction with the operating system, whether through command line utilities, compiled programs, or the broader software ecosystem. In an operating system such as Linux, user applications normally run in user space, a non-privileged domain that lacks direct access to critical hardware components or system-wide resources. This is vital for safety and stability, ensuring that a misbehaving program cannot inadvertently corrupt memory belonging to other processes or the kernel itself. Whenever a piece of user software requires interaction with a sensitive resource, like the underlying file system, inter-process communication channels, or hardware devices, it cannot simply manipulate those objects directly. Instead, it has to ask the kernel for help. This request is formalized as a system call. A system call is effectively a carefully monitored entry point. When invoked, it instructs the processor to switch from user mode, which is unprivileged, to kernel mode, which is privileged, letting the kernel carry out the requested action on behalf of the process. Through this design, the operating system retains ultimate control over the hardware, all while allowing user processes to accomplish tasks ranging from file manipulation to creating new processes. The importance of this approach cannot be overstated. It strikes the ideal balance between powerful functionality and robust isolation. In many development scenarios, programmers do not manually trigger system calls by name. Instead, they write in a higher-level language such as C, utilizing the standard library functions that, under the hood, handle the low-level work of assembling the required system call arguments and placing them in the right registers. As an example, when a C program calls printer, it may rely on the writer system call to send data to standard output. This bridging role played by libraries helps shield developers from the intricacies of system call invocation. One of the most frequent ways in which programs interact with the operating system is through file manipulation. The ability to read, write, open and close files forms the backbone of everyday computing, from the simplest text editor to the largest database systems. Linux, in particular, offers a suite of fundamental file-related system calls, each with its own role and set of parameters. Although many developers now rely on higher-level libraries, understanding these underlying calls provides crucial insights into how data ultimately moves between disk and memory. Open, read, write, and close enable controlled file access. File descriptors serve as integer references into kernel-maintained tables. These system calls let applications securely interact with the file system, allowing for structured I/O while preventing resource misuse. Linux uses fork, execp, and wait to manage processes. Fork duplicates the current process. Execp replaces a process with a new program. Wait and waitpid allow a parent process to pause and synchronize with its child. These calls ensure process coordination and allow shells and scripts to run efficiently. File descriptors, they map to files, sockets, and pipes. Descriptor 0 is steady, N, 1 is stout, and 2 is std. Bash, redirection, and piping, use these descriptors to route data efficiently, but failing to close file descriptors, that can lead to resource exhaustion. Bash, as it turns out, relies heavily on system calls like fork to create child processes and exec to run commands. It uses open for file redirection and pipe to connect commands. These interactions, they happen with every single command you type. Start, if you will, with tools like Strace to see system calls in action. Build utilities in C that use open, read, write, and fork. Then perhaps make a simple shell that uses fork exec, and finally explore sockets and IPC. These exercises, they reveal how system calls underpin Linux systems. System calls, well, they offer controlled access to privileged kernel features. They uphold system integrity, performance, and modularity. Mastering them, you see, gives you the power to understand and build efficient Linux applications, from CLI tools to multitasking demons.